Now, visualizing a linear model whenever you're dealing with a case that is somewhat simple like this, just one predictor variable, is actually very straightforward. We've got our plot of our data here, FM index through time, and all we need to do is add AB line, which is a function that draws a line from point A to point B. But this function is really nice because if you just feed it the model object, it pulls out that kind of start and end point for you. And so I can say just plot AB line of SACMod and make it red. And if I run that, we've got our model fit. Very straightforward, very easy. A nice line here plotted ranging from across the range of our date values and kind of allowing us to see visually what this model is. Now this model, if it hasn't clicked for you yet, is really just the equation, and you, instead of just feeding in one value to x, like 2200 as we did before, you feed in every value of date, and all of those different values together are what make up the line. And so if you don't believe me, you can also just use the points function and say, okay, the points function, draw a point at an x value of 2200. And remember, we calculated the FM index at the year 2200 BP. And so at that x value, plot the FM index that we calculated. Let's make it blue so we can see that point. If I run that, we've got a point now on our figure that represents the calculated FM index that we got, negative 0.305, right? And it's falling right along that red line, along our model fit, because we could just simply plug in, instead of 2200, then 2300, and we would get a slightly lower value right around here, because that's what this red line is. It's just that equation extended across the range of our predictor variable. And so this is probably more important than knowing how all of the coefficient stuff works, because this is a visual representation of the model equation. This is kind of a quick, simple way that you can pull up a plot and show somebody what your model is doing. But as we discussed in kind of the lecture on linear models, this model fit here is the deterministic part of the model, right? There's two different parts to a model. You've got the deterministic and the stochastic part. The deterministic part is that equation simply predicting what the value is. The stochastic part is a representation of the fact that there is randomness, there's noise, there's stochasticity around that model fit. And it's important to visualize that too. And the most common way to visualize that is confidence intervals. This idea of plotting a 95% confidence interval showing some approximation of the range of values around this deterministic model, around this model fit. Plotting confidence intervals is a little bit trickier. It requires a few more steps. There are some functions and packages out there that can make this easy for you. But using just base R, the way that we would do this is first we need to make a data frame. We'll call it new x, because this is going to be a data frame of all of the values across the range of our predictor variable. So we've got date, but in our data frame of SAC data, we only have 9 different dates, right? 9 different points for which we have information on the FM index. And when we're plotting this red line here, and the confidence intervals that go with it, we don't actually just want that to be based on these 9 points. We want to interpolate and kind of infer what's going on between those points, beyond those points. That's the point of linear modeling. And so we're going to make a sequence of data that spans that predictor variable. For what we're going to do, it needs to be in the form of a data frame. So we make a data frame with a column called date, and we're going to then make a sequence of values from 4,000 to 0. And I'm going to say, use this length.out argument to say that I want 100 points between 4,000 and 0. So give me a sequence of 100 points from 4,000 to 0. Put that vector into this date column of the data frame new.x. So if I run that, You can see here that we've got a single column, a vector of dates, right, ranging from 4,000 all the way to 0, and there's 100 different numbers here. And so this is kind of the fake predictor variable that we're going to use to predict the FM index values based on our model equation. So now let's make an object called pred_y, and this is what we're going to then use, or rather, this will be the result of our prediction based on the model. We're going to use this predict function, which actually does what we did manually when I had you calculate what the FM index for 2200 BP is. The predict function can do that for you. And here we're just going to use it to say, all right, take the SAC mod and predict across the values of new.x. So we're saying take the new.x object, which is this series of 100 values spanning 4,000 to 0, and tell me what the predicted y value, the predicted FM index is, based on our model equation, based on our model there. In addition to just that new data argument, which is where you feed it the new.x object, we also need to tell it that we want to predict confidence intervals. We do that like this. Interval equals confidence, in quotes, and specify that we want these confidence intervals to be 95% confidence intervals. So we use the level argument to be equal to 0.95. Again, checking out the help page for predict will tell you all of this information. Now if I run this, we now have pred.y, which is a nice object that contains 3 columns: fit, lower, and upper. We've got the model fit, which is what we've already plotted in red. We've got the lower confidence interval and the upper confidence interval, lower and upper 95% confidence intervals in this case. And so now we've predicted those confidence intervals, and we can add them to our plot. We can do that using the lines argument. We say pred_y, which is our object, and looking at those different columns, we can index within that. We have to index within that, and pull out first the lower confidence interval. So I say take pred_y and give me all rows, but only the second column. And so with pred_y, then plot that as a function of our kind of fake predictor variable, new.x, and you have to specify $date because new.x is a data frame, and you've got to tell it which column in the data frame. Even though there's only one, still specify $date. And let's make this line not solid. Since we have got the main model fit being solid, let's make this a dashed line, which is line type 2. LTY argument is line type. And then let's make it red as well, just so it matches the predicted model fit. If I plot that, we've got a nice lower confidence interval there. Now we can copy this code to save us some time, but now change it from indexing pred_y from the second column, make it the third column, because as we saw before, right, when we look at pred_y, we've got the fit, the lower confidence interval, and then the upper confidence interval. The upper is in column 3, so we need to index for column 3. So it's all rows, comma, the third column. We're still plotting that as a function of new.x $date of our kind of fake date object. And voila, there's the upper confidence interval. So now you can kind of see not only the model fit in the solid red line here, but you've got some sort of estimate of the stochasticity associated with this model fit, this 95% confidence interval. And so this is really a quite useful way to visualize linear models in a lot of cases. When you're dealing with categorical data, as we were before, or categorical predictor variables, I should say, plotting the model fit like this isn't always necessary. You can do it, but it's not generally done with t-tests and ANOVAs. Sometimes it could be, and indeed sometimes it probably should be. But this is a little bit more common when you're dealing with a non-categorical predictor variable like date in this case, that you would plot these things. And note finally that we've got our nice model fit here with the confidence intervals. We need to report on this model. let's pull up the summary of the model object again, since we've moved on from it. Let me do this. And so we've got our intercept, our date back. And so as with the other models that we've looked at, right, the estimate is not the only thing that we really care about. Each of these estimates has associated standard errors, and those standard errors and estimates are then used to calculate a t-value in this case. And based on that t-value, we get a p-value here. As I've said before, these p-values on the coefficient estimates are not necessarily what you want to be looking at. They're expressions of whether the coefficient estimate is significantly different from 0, based on the estimate itself and the associated standard error of it. Once you start getting into slightly more complex model types, these p-values are not going to be what you're really looking at in some cases. In this case, it happens to be that the actual p-value for the model is the same as this one. Right here at the bottom, this is the model p-value. It's the same as the date p-value in this case because, again, it has to do with the intercept being kind of the 0 value, and we're going from there, comparing it to that, and so it works out that it's kind of the same in that sense, that it's different from kind of a model that might only have that intercept value. But regardless, this p-value then is our model p-value. That's what we're going to want to report. And of course, associated with the p-value, we need to report the test statistic, which is the F statistic here, which is 22.61. We've got 1 and 7 degrees of freedom. And so when we're reporting this, we can say something maybe like our, there is a, what would it be? There is a significant, let me write this down. There is a significant relationship between the FM index and date. And then in parentheses, you could say F with degrees of freedom 1 and 7 is equal to 22.61. And then say P is less than 0.01 in this case, because our p-value is 0.002. This would be a good way to kind of summarize that model output. But, of course, there's actually more to it. And now we're going to talk about this idea of the R-squared statistic, which is reported here in all of these models as well. The R-squared statistic, as we discussed in the lecture on linear models, is a representation of the proportion of variance in the response variable that is explained by including the predictor variable in our model. So in this case, it's the proportion of the variance in FM index that we can explain using date. The R-squared value here is 0.7636. It's reported here as a multiple R-squared value. There's also the adjusted R-squared value, which is slightly different. This one is a slightly different thing. It's a penalized R-squared value if you have a bunch of different predictor variables in a more complex type of model. We're not dealing with that right now. We're looking at the multiple R-squared value, which is 0.76. So what this means is that 76.36% of the variance in FM index can be explained by our model that includes date as a predictor variable. That's the R-squared value. That's how you would interpret that. And that is really good. R-squared values range from 0 to 1, and the higher you can get, the closer you can get to 1, the better off you are. And so when we are reporting the result of this model, we can say, yeah, there's a significant relationship between the FM index and date. That's what our p-value for the model is telling us. But we can also say something about the R-squared value. We could say, because as I said, an R-squared value of 0.76 is quite good. That's actually a strong relationship. So we could amend this to say not only that there is a significant relationship, but there is a significant and strong relationship between the FM index and date. And in this case, what we want to do then is report our R-squared value of 0.76 along with the p-value. And the way I do this is I'll say like R-squared equals 0.76. I'll put a semicolon and then the F statistic, comma, p-value, because the F and the p-value are related to each other, and the R-squared is somewhat different in this case. So reporting them all here as such would work. Of course, there's other ways to report this. You could mention that this is, in this case, it's a bit misleading because we've reversed the x-axis. This is a significant and strong negative relationship between FM index and date. This model, even though it's increasing from left to right, if you'll recall the actual data, we flipped that x-axis, and so instead of having 0 at the right, 0 is actually at the left. As far as our model is concerned. So this is technically a negative relationship. But if you understand the date as this, in this sense, you can imagine that instead of being 1,000, this is negative 1,000. Instead of being 2,000, this is negative 2,000. That would make this a positive relationship here. So it all depends on how you've structured the model and how you want to interpret this. But this is a significant and strong positive relationship if you have the axis this way, or a negative relationship if you have it the other way. Between the FM index and date. Now I'm saying this is a strong relationship based on the R-squared value, and that's because generally with these R-squared values, if you've got something between 0 and around 0.3, that's weak. That's really not much to go on. If you then have an R-squared value between 0.3 and 0.5, you can call that weak, but that's potentially still a reasonable relationship. There's something going on there. If you've got values from 0.5 to 0.7, that's a moderately strong relationship. Definitely something going on there. And if you've got 0.7 to 1, that's a very strong relationship. Anything above 0.7 in a lot of cases is good. Now there's a couple different caveats with this that we'll get into later, but this is the general kind of structure for how you want to describe your model. If it's a weak relationship, a moderately strong relationship, or a very strong relationship. In this case, with an R-squared value of 0.76, we've got a very strong relationship. You could also say something in your model, kind of reporting your model results about how your data explain 76% of the variance in the FM index, and then report your R-squared. You could say something about even date having a negative effect on the FM index or a positive effect, whatever it is, and actually report the beta value. If you indicate the directionality, you can say that it is a, for example, negative relationship, and then in parentheses you could say beta equals negative 0.00067 or whatever our value was. That's something that you can also do, which gives you kind of a quantitative representation of the direction of the model for somebody to see it. Now when you're plotting the model, they don't necessarily need that because they can see the direction based on your plotted model fit, but sometimes you don't plot the model, in which case reporting a beta coefficient can be really useful as part of your model kind of description here. And so, yeah, that's a lot of information about how to report on the values of this. But generally speaking, throw in the p-value and the test statistic associated with it. Throw in your R-squared value, which is really important. And perhaps describe also the directionality of your model. Plot it if you can, but throw in the beta coefficient if you can't, or it's not worth plotting. And that's generally enough information to convey to somebody what exactly it is that your model looks like and what it's doing and what it tells you.